finite element demonstration with LIFU. And then at the conclusion of that, I hope that you learned something about fatigue and that is clear to you how this could be applied in practicality. Through some problems that you'll be working through, I think we'll try to connect those areas for you. But for now, enjoy the Abacus tutorial.
Hello everyone, welcome to Finite Element Method tutorial. Today we are going to learn how to use Abacus to simulate the fracture mechanics and obtain the energy release rate. So here's our problem statement. There's a plate of 10 by 10 inches and there's a crack in the middle of the plate. Since the geometry is symmetric, we only simulate half of the plate. And the half crack length is 0.1 inches and the thickness of the plate is 1 inches. Material property is 10 megapsi and Poisson's ratio 0.3. The plate is under tension of 2000 psi on the direction of the mode 1 crack opening. And we're going to use two methods to obtain the energy release rate. First, by the J contour integral. The second method is by the strain energy derivative. So we roughly estimate the derivative as the by adding a small change of the crack and then compute the deviation of the total strain energy. And let's see how do we apply the Abacus analysis. Create a part, 3D shell plate. So total length 20 and half of the thickness, so it should be 0 minus 5 to 5, 5. So this will give you a 5 by 10 plate. And material property is elastic material property, Young's modulus 10e6 psi, Poisson's ratio 0.3. So assign the section, shell element, and then homogeneous, and the thickness is 1 inches. And then assign the section. We don't need to create set down. Assembling, create an instant, independent. And now we need to create a crack in the plate, and also for better mesh the plate, we need to partition the surface. Use this tools and select the right edge. And before we actually did that, we can create some point here. First point is this point. Second point is this point. Now we can create a construction line for later, better to draw our sketch. One is horizontal, one is vertical. Now we can draw our crack. Our crack should start from the very left end and extend by amount, and use the dimension tool to control the length. This should be 0.1. And then we need to draw the contour circle. So to draw the contour circle, we select this end and select another end on the horizontal construction line. Please make sure that your circle, the second point, is on the construction line for later, so that later it's easier to make partition. So now use the dimension tool. Let's make a 0.02 in radius. So this will be our contour line. So we make another circle. Again, your second point should be on the horizontal construction line. And make the radius of this 0.4. So this is just for mesh. Later when you do the mesh of the plate, this circle will make your mesh looks better. And then for we draw a rectangular just for mesh. So use the dimension tools. So this line and this line, the dimension for this, let's just make it 0.06. Similarly, this, let's also make it 0.06. And then the distance between the very right end and the first construction line, let's make it 0.2. Oh, sorry, 0.2. So then from this rectangular box, we draw the line that is vertical to the entire plate, just for plotting. All the way to the end. It should show a V here, means it's vertical. And click end, and then use this again, joining this point and some point on the top. And make sure that it's vertical. Once it's done, you should obtain some geometry like this. Sorry, I haven't finished the sketch. So if you want to change your sketch, go to your partition, assembling, features, partition, select sketch. And then one thing we haven't done is we need to finish this line from the center of the circle all the way to the end of this line. And since you create a thing, you can right click the features, click regenerate. You see that the circle was cut into half. And this is the shape we need for assembling. Then the step, we create a step of general static. The increment, we can do just 10 increment and increment size 0.1 and make it fixed. And then in your field output, originally you have a lot of field output, but here, since we're not focusing on field output, probably we just need the von Mises stress and the displacement, U. History output is what we need. So we can create a history output here, which should be related to energy. And inside the energy, choose the ALLIE, which is total strain energy. And originally, we unclick the energy. Instead of energy, we will select the crack. We haven't created a crack yet, so we'll go back to the crack first and then assign the history output. So in interaction, zoom in a little bit. In your special crack, assign scene and select the 3 part that you assume that is your crack. After you click the down button, you should have a dark line here. In your special crack, create the crack from contour integral. Select the integration area, so select the top and bottom circle. And then select the crack tip, which is the center of your crack. And then use a Q vector for the propagation direction. So your crack propagation direction is pointing to the right. So you see a blue arrow pointing to the right. And then in your singularity, since we are doing only linear material property, linear analysis, so we do elastic analysis, so we make it 0.25. If you do plastic, you can make it 0.5. And then single nodes collects element side. Now you have the crack, go back to your step, and in your history output, the first output, instead of energy, we select the crack here. And crack 1 and then number of contour, make it 3, and choose a J integral here. So then we can go to the load part. First, we need to assign symmetric boundary condition. So in your initial symmetric, select the left boundary. Hold shift, select all of that. And select the X symmetry. Then is the applying the load. In your step 1, create a shell edge loading. Select the top surface. We can use the biangle and then select the bottom and the top so that you don't need to select 4 parts. You just need to select 2 parts. And the magnitude, since the shell edge loading is kind of the same as the pressure, so if you want tension, you need to enter minus 2000 here. And the traction is defined on the undeformed length. If you see the arrow is pointing outside the plane, then it's okay. Then it's good. Then go to the mesh part. So first select this 3 region, because this 3 region is just rectangle, so you can assign that as structure. And then select this 4 region. This 4 region are all circular region, so we can assign that as sweep. And the rest is the red region is actually between the circular and rectangle, so you cannot use either structure or swap for that, so we just leave it free. Now assign global seed. Global seed we put 1.1 inches long. We can see the seed for the circle is too coarse, because near the crack tip we want it to be very accurate and more element. So we assign use by edge angle instead of individual. And then choose the outer circle and the inner circle. And select by number. Instead of 4, we actually make it 10. So it'd be way finer here. Also select this, instead of by angle, let's change it back to individual now. So select this portion, hold shift, this portion, this portion, and this portion. This 4 portions should be at the same length. And we can make it by number and change it to 5. So that near the crack tip is pretty fine. Now we can draw the mesh. You can see near the crack tip and around the crack tip is actually has way more element than outside the region. So now we can go to our job and call it plate 1 and submit. It doesn't take long time since this is just a 2D element. So while it's running, we can go back and change our model. As long as you see the input file was written, then it's good to change whatever you want. So now go back to your features, partition face and sketch. Now we need to For the second method, we need to increase the crack by 0.02 inches, which means the value we enter here instead of 0.1, we can delete that. We actually can select that. And make it closer to the surface. Yeah. I can see that it represents this length. And instead of 0.1 here, we actually, we can delete this one and then redo this dimensions. And we make it 0.12. So 0.02 millimeter, 0.02 inches more than previously. You can see the circle is moving to the right. And then click down. And then in your features, right click and regenerate the result. And it should be here now. Now, since your partition has changed, so everything needs to be reassigned. Let's go to the crack first. Assign the seam. Seam is automatically assigned from the beginning to the center of the circle. And then in your crack, you can see everything is correctly assigned. Your crack is here, your crack tick is here, and your pointing direction is to the right. That means for your crack, you don't need to change anything. And let's check this, all the steps. The steps should be fine, and the output also should be fine. And your load, symmetric, and the force is also applied correctly. The only thing that matters is the mesh. So you need to assign the mesh again. Now it moved to the right a little bit. So everything is fine. Go to your job, create a new one, call it plate 2. And then submit the result. And now we can see the plate 1 result. Let's see the stress first. Von Mises stress. You can see the von Mises stress distribution, the stress concentration area, the butterfly shape of stress, and the crack opening. You can see here is still a little bit coarse. If you want it to look better, you can make a finer mesh for this part. Here, I just want to save the computational and power. So if you feel like your result offset a lot, you can make it finer. So to show the result, go to your XY data and create a data from the history output. You can see that we have the J integral here, and we're doing mode 1 here. You can see the J integral. And to see the value, we can use the Q-read and then probe value. Select the ending point, which means our value for the J integral is around 0.113 here. If you make the mesh finer, I think it will closer to 0.12. And let's see from the other direction, if you see the energy, what's the result? So here you can see the energy, total energy. Again, we use a probe value for that. And it gives you 10.0061. 10.0061. We just use calculator to remember that value. Now we can see, go back to see the that is has 0.02 inches increment in the crack. So here we create XY data from history output, and let's plot the energy, and then again probe value for the ending point. This is 0.0086. So previously it's 0.0061, and that is 0.0086. So we have 10.0086 minus 10.0061. And this value divide by, according to the formula, divide by the increment of the crack, which is 0.02. Sorry, this calculator will won't follow the algorithm rule. So we do 0.0025 divided by 0.02. So it's 0.125. So it's very close to the previous one. 0.125 should be a correct value. So, but our J integral is a little bit offset. So let's see if we find the mesh, whether we can change it back or not. So go back to assembling the same as what we did before. Here, instead of 0.12, we delete this one and redo this dimension. Change it back to 0.1. And regenerate the features. And in your mesh, you can see that it's not mesh now, so just mesh it. And we want it to be finer for all the region that is around the crack. So for left and right, we can make it 5 of that. And for top and bottom, hold shift, select top and bottom, we make it 10. And for the middle, for this one and this one, we make it 5 or even 10. Just leave it 5. Now we can do the mesh. Now it's finer to previous one. You can see how much it can improve your result. So go back to your job and create another one, call it plate 3. And then submit that. So you can also see the monitor here. Monitor start from 0.1 and suddenly go to 1. So it's very fast for this analysis. You can try different mesh. So now if you see the hole, the opening is more natural, like it follows a natural curve, not like previously it's kind of digitized. So if you see XY data from the field output, from the history output, and J integral for the first one, and use the probe value for that. You can see 0.1247 is very close to the energy derivative result, which is 0.125. You can even make this more close to whatever you more close to the actual solution by finer the mesh. So this is how do you apply abacus to obtain the energy release rate. Hope that we compare the J integral method and the strain energy derivative method, and both of them shows the same result, and it's the same as theoretical calculation. And the only difference is for J contour integral around the crack, the mesh side should be relatively fine to obtain the reasonable result. So that's all for this video. Hope that you can learn something.